Hello, welcome to ECE tutorial series. In this lecture, we will talk about drift current, diffusion current, drift velocity, Einstein relationship in for semiconductors, and what is degenerate semiconductor, what is non-degenerate semiconductor, what is the principles of this semiconductor, principle and applications, and we will talk about diode. What is diode and diode basics only, not that much in depth. We will talk about later in this next video. So first we will talk about what is drift current. uh, when we talk about semiconductor material or when we talk about any material in which like some material is there or semiconductor material, we can assume semiconductor material is there in this due to applied voltage some electric field will generate, and this electron will drift from due to influence of electric field. This electron will drift in this direction. So this drifting of electron will flow a current in this direction. Current flow will be in that direction, so that I will be flown is called as drift current. And drift velocity it at which this electrons are drifted. Drift velocity Vd is given by mu into E, where mu is the mobility. Okay. And when we talk about diffusion current, when any semiconductor material, diffusion current, we are talking about diffusion in any semiconductor material. When diffusion occur means concentration gradient will occur. When some concentration difference in concentration, assume this is x equal to 0 with the distance is equal to epsilon. With the change in distance, the concentration of electron will decrease. Concentration gradient, and concentration gradient will be given by dn by dx for electron, and dp by dx for hole current due to hole. So for diffusion, actually electric field is not required. We have seen here there is no voltage condition. Electric field is not required. Here what is required here, dn by dx should not be 0. Okay. So if we know about current charge density J is equal to I by A. This is called current charge density. So, and what is the formula of this conductivity is given by q n into mu n. Okay. And q mu n in case of n, and p for q n mu p, or you can say p, q p mu p. Okay, this is the conductivity formula. Okay, J equal to I by A. So J is approximately q n mu n plus q p mu p into E. You can say this is the formula for current charge density in case of both majority and minority carriers. Okay, in n type, what is the majority carriers? In n type, majority carriers are electrons, and in p type, majority carriers are holes. Means current produced due to holes in p type. Now one more topic is there here, in which we will talk about this formula first. This formula, what is the dn by dx, what is the dp by dx? So we can say dn by dx is proportional to, here concentration is proportional to this current charge density is proportional to dn by dx. Okay, and this Jn is equal to q, this Jn is equal to, sorry here, Jn is equal to q into dn by dx. This is the formula for current charge density for diffusion constant with the dn equal to diffusion constant. Okay, dn is the diffusion constant here. Or in case of Jp, in case of holes, there will be minus sign, dp by dx. Okay, these are the two formula to remember. Now we will talk about mass action law. Now we will talk about mass action law first. Mass action law. Okay, this will state that the product of majority carriers, which is an minority carriers, and minority carrier is constant at fixed temperature and is independent of donor and acceptor impurity added. Means product of n into p is equal to ni square. This is the mass action law. N is the number of electron in conduction band, p is the number of holes in valence band, and ni is the intrinsic carrier concentration. Okay, this is the formula to remember. One more formula we will learn, which is Einstein relationship. This is the formulas to remember. For example, here Einstein relationship will state that mobility mu of electron or holes and diffusion coefficient of electron and holes dn by dp is given by d by mu is equal to Vt. This is the Einstein relationship, in which what is the d? D is the diffusion coefficient. Okay, diffusion coefficient, and mu is the mobility. Okay, d by mu equal to mu p. So we can say dn by mu n equal to Vt is equal to kt by q. Here Vt is given by kt by q. Okay, in case of electrons, and in case of holes condition, dp by mu p is equal to kt by q. Okay, these two formulas for Einstein relationship is there. Here now we will talk about degenerate and non-degenerate semiconductors. Degenerate semiconductor when dopant atoms are more and more. Dopant atoms are more means level of doping is high. Level of doping is very high, so that material acts like metal. Semiconductor material also acts like metal. This is the important point. Okay, so where we can use degenerate semiconductor? So degenerate type semiconductor used in to create the condition of laser diode. Like laser diode, we will talk about population inversion. Population inversion. This is the mechanism required for laser diodes. Creation of laser diode. This is the basic principle. So here degenerate materials are used. We talk about non-degenerate non-degenerate semiconductor means the concentration of doping atoms added is small as compared to host atom. Host atom means what? Host atoms. Host atom means what? Like density of the semiconductor atom. Density of semiconductor atom we can say. Okay. So these are the non-degenerate semiconductor. Application of non-degenerate. Actually, non-degenerate semiconductor are used in modern electronics. Like where it is used for optoelectronic devices. Optoelectronic devices, or it is used in sensors, LED, photovoltaic cells, okay, diode, and transistor, and many more applications are there, but we are discussing about this one only. Degenerate. When we talk about this degenerate, so how it will be, like for one formula is there for how it's like a metal. There was like conduction band and valence band was there. So Fermi level equation is given by EC minus KT ln NC by ND. Okay. If we dopant atom are more and more, means this ND is high. Dopant here we discussed. If dopant atom are more and more, and level of doping is high. Level of doping high means this parameter is high, and if this parameter is high, this condition may, there is a chances that this will become more negative. So EC minus some negative value will become this, something plus value will come. So ET is the conduction. So here is valence band and conduction band. So EC plus means this EF will be shifted to this EC plus, means it will overlap with this. So what is the condition for this valence band overlap with this? Okay, so this is the condition of metal. So these are called the degenerate semiconductor. This is the condition, degenerate semiconductor. This is the condition. Okay, so this is for today's videos, and we will talk about diode, in which in later videos we will talk, in which some brief idea I will give you. P and N type, both material are added simultaneously. Both are added simultaneously in a wafer. So what will happen in P type? Majority carriers are holes, and a small amount of electrons are also there. And here N type, electrons are more, majority carriers, and holes are minority. So at zero temperature, what will do? This will diffuse from here. This will move somewhere. So this will try to neutralize each other. So this will call us diffusion current, and diffusion current will generate. But if we apply some potential here, so what will happen? Some barrier, this potential barrier will be generated here, and this wall will be created where electric field is generated. Okay, electric field in this direction will be generated. Okay, so some cutoff potentials after 0.7 volt, this new potential current will automatically rise. Why? Because due to make of this wall, this electron will be shifted here due to this plus charge, and if this is greater than 0.7 volt, then this electron will cross this barrier, potential barrier, and will generate a current. Okay, electron flow direction will be in this direction. Okay, so this is the condition for vi characteristic of the diode. Okay, this will talk later in this in more videos. Okay, thank you.